Associate Professor Bayden Wood, Director of the Centre for Biospectroscopy at Monash University. Bayden Wood, thanks very much for talking to us this morning. Now, you've come up with a new method of detecting and diagnosing the disease. Tell us a bit about that.
Yeah, good morning, Andrew and Miriam. Thank you very much for having me along. We've been just recently come back from the PNG, where we had the most amazing scientific exposition of our lives, really, where we applied this new technology, it's called infrared spectroscopy, to actually diagnose and look for these patients called asymptomatic carriers. Now, these are people that have malaria, but they don't actually show the symptoms of the disease, that being fevers and chills and these type of conditions. So our technology is an infrared-based technology. It's very portable, and we were able to carry it into these villages and actually take blood samples with the aim of developing models to actually ultimately diagnose malaria and detect these asymptomatic carriers. And by doing this, we can actually identify these people, treat these people, release them back into the community, and in that way actually stop the spread of disease through the villages and the greater population.
Just looking at that specific method that you're using, spectroscopy, now this is essentially using light. Just tell us a bit more about how that works.
Yeah, it's a bit like the Star Trek analogy, Andrew. It's sort of using light as a way to diagnose disease. In our case, it's infrared light, and what infrared's associated with, it's associated with the vibrations of molecules. So what we do is we use infrared light, we excite the vibrations of these molecules, and we get what we call a spectrum, which represents a chemical fingerprint of the disease that we're looking at. So in the case of the malaria parasites, they've got their own DNA, their own RNA, their own proteins and lipids, and we're essentially detecting those and getting the chemical bands on our spectrum, which we then use to actually model and diagnose people with the disease.
So you have a readily portable kit?
Yes, it's very portable. We can actually hike it into the field. It runs off a 12-volt battery. We ran the spectrometer off the battery, plus a little centrifuge, plus our laptop, and we did it all point of care in the actual villages there. So it was a very confronting experience for me. I'm a clinical scientist, so we don't really get to see people with malaria, of course. We just get usually samples with parasites in them, but to actually go in the field and see people with malaria and actually get that experience firsthand was really valuable for us. And I suppose the other really valuable thing was seeing how the technology actually stood up in the tropical environment under these really harsh, high humidity conditions. And it did really well. It didn't miss a beat. We analysed over 230 patients and brought back some great data to actually do and test back here in Australia.
So potentially far-reaching consequences in those remote areas, such as the Pacific region and also to our north. Also, of course, Africa, where malaria devastates so many communities. So you're talking about going into these communities, and would you be testing every person?
Yes, that's right. We actually go into the village, and the whole idea is to test every person in the village and see if we can detect these asymptomatic carriers. And once we detect them, we treat them, and then that's a way of actually stopping malaria spreading through the villages. I don't know if the Australian population is actually aware of this, but in Papua New Guinea there's probably 1 million suspected cases of malaria, 900,000 to 1 million cases. So it's a serious disease. These are our nearest neighbour, and there's a lot of people suffering with malaria there. It's endemic to the region. So hopefully our technology can actually start to have an impact in these type of areas and ultimately go to saving lives.
And as you say, so you're really trying to target these asymptomatic carriers, people who don't actually develop the disease. They're carriers, they're reservoirs, if you like, for the disease.
That's exactly right.
So what would you then do? You identify these people. How then do you treat it?
Okay, you treat malaria in the same way it's normally treated, usually using some type of anti-malarial, whether it be doxycycline or primaquine or one of the artemisinin, one of those types, depending on the actual Plasmodium species. But the idea is to treat the people there, and then they can go back into their communities and they stop spreading the disease around because they get bitten by mosquitoes still, but they won't be harbouring the parasite in their bloodstream. And it's really about trying to detect parasites in the bloodstream at these really low levels of parastemia.
But ultimately, what would you like to see? Would these kits be rolled out to all these areas which are in need of identification of the disease? If that were to happen, what do you think the end result would be?
Well, I think what we're doing as well with our kits is we're also using and look to other diseases as well, including anemia, including diabetes, and also been applying the technology to HIV and hepatitis B and hepatitis C. So what we ultimately hope to have is a multi-disease diagnostic that we can actually take into the field and do multiple disease tests at the same time. These tests, the equipment is it's relatively cheap compared to other equipment of similar sensitivity. So what we really hope to do is be able to take these into the villages, diagnose everybody in the village and move it along to the next village. And our ultimate aim is to really try to develop these technology and hopefully commercialise this technology to the point where we can actually take it to other countries as well, where malaria is also a huge problem.
It is a very exciting development. Associate Professor Bayden Wood, thanks very much for joining us.
Thank you.